So our next speaker is Nayana AJ, who's going to continue the conversations about LF bots.
Hello, everyone. I'm Nayana. I'm a postdoc at UC Berkeley. And today I will talk about the most luminous fast blue optical transient, AT 2024 WPP. We carried out an extensive multi-wavelength campaign on this target. I will focus on the X-ray and radio side of the story. Natalie Lebaran led the optical UV-IR observations and modeling, and she also has a poster on her results in the meeting. So fast blue optical transients, they are characterized by rapid timescales and peak luminosities reaching about 10 to the 44 ergs per second. They show persistent blue colors and featureless spectra, and together they are in tension with traditional supernova models. Luminous F-bots, LF-bots, they are an even rarer subclass of F-bots with extreme luminosities about 10 to the 43 ergs per second. They also show bright X-ray and radio emission. They're intrinsically rare with a rate of less than 0.1% of that of core collapse supernovae. Now, the prominent examples include the prototypical event AT 2018 COW, CSS 1610, AT 2022 TST. While they are in tension with traditional supernova models, other progenitor models include engine-driven models or CSM interaction wherein shock breakout into a confined CSM powers the luminous emission. Now, there are about 13 LF bots detected, out of which there are only 7 events with detailed multi-wavelength follow-up observations. AT 2024 WPP is the latest addition to the LF bot population and is the brightest LF bot to date, reaching peak luminosities about 10 to the 45 ergs per second. It's at a distance of 411 megaparsec. For comparison, the prototypical event 2018 COW was only at 60 megaparsec. So due to its extreme luminosity, we could carry out a broadband campaign covering UV, optical, IR, X-ray, and radio observations from a few days post-discovery to about 300 days. There are also other teams worked on this event, including Pearly, Omad, and Liu, broadly reaching similar physical interpretation. These are the main results from the UV optical IR campaign from Natalie's work. It shows a optical spectrum, which is a thermal continuum with high temperatures above 30,000 Kelvin at peak, and it maintains a high temperature throughout our monitoring. The peak, the rise time is about 4 days, and that implies a ejecta mass less than 1 to 2 solar mass. WPP radiated a total of 10 to the 51 ergs in the first 45 days, which is in tension with typical core collapse explosions. The spectra remain featureless up to a month and then shows very faint hydrogen and helium features. On top, while the overall SED is consistent with a black body, there is an IR excess roughly at day 30. This is also seen in 2018 COW, which can be explained either by reprocessing by pre-existing dust or free opacity effects by a medium above the optical photosphere, which could also lead us to infer a radius, a density. Now, we carried out X-ray observation using both soft and hard X-ray facilities to cover the broad energy range. We got a very high cadence count rate light curve using the SWIFT geo program. And together, we obtained 5 epochs of broadband X-ray SED covering 0.3 to about 79 kV. In the radio, again, we use multiple facilities to cover sub-gigahertz to millimeter bands using GMRT, Meerkat, ATCA, and ALMA to obtain broadband SED. Now, these observations are not intrinsically coordinated, as in they are not coordinated at the facility level. So we had to coordinate by ourselves to make sure that these observations are done near simultaneous. Now, these are the X-ray spectral and temporal properties. of WPP. So it shows luminous, roughly constant emission in the first 5 days, followed by a phase of rapid decline, goes up to 30 days. After that, it enters to a phase of major rebrightening, peaking around 50 days. Now, if we look at the spectral evolution in the top panel, it starts with an initial soft spectrum of (10⁻⁻⁸), gradually hardens with time with extreme spectral hardening at day 50, which moves back to a soft state after that. Now, together, the entire spectral evolution indicates that there are possibly two spectral components defining the overall spectral behavior of WPP, where the hard component's contribution is increasing towards the time up to 50 days. Now, what could cause such a spectral and temporal evolution? So typically, transmission of radiation from a high energy source through a ejecta with variable optical depths to photoelectric absorption and Compton scattering can produce such signatures. And in the right panel, you see a set of X-ray transmission spectra from such a source for varying Compton optical depth. Also, we see hard spectral index as late as 50 days, which is incompatible with fast cooling of non-thermal electron. So certainly the X-rays are not coming from the shock, but from a central engine. Coming to the radio evolution of this source, now radio emission from F-bots or LF-bots are understood to be shock-driven synchrotron radiation. However, the spectral evolution of WPP is unique. As you see in the right panel, two main features are one, the extremely rapid rise in the millimeter band at early epochs between 17 and 32 days, followed by a more standard evolution at later times. We also see a signature of a spectral inversion at late times, which are marked as circles. If we look at the shock parameters from this SED modeling, it shows a rapidly growing shock with shock velocities reaching up to 0.4 C at roughly 73 days, with increasing shock energy coupled to this outflow. Now, again, looking at various possible physical scenarios that could produce such spectral evolution. Either it can be an apparent effect as that we would expect in an off-axis scenario where initially the outflow is beamed out of our line of sight, and as the jet decelerates and spreads, we see more and more emission coming to the line of sight. Or there can be effects like cooling of synchrotron emitting electrons, which initially suppress the flux, or the shock propagating through a dense medium. Now, looking at the off-axis scenario, if the SED evolution is due to an off-axis effect, we can calculate the shock deceleration timescale by which we would see the emission peaking. If we plug in the energies and the typical densities of LF bots, we get a deceleration timescale and corresponding time for the peak of the light curve to be less than a day. And we see the light curve peaking in a month timescale, which means for typical parameters, off-axis will not explain what we are seeing. Similarly, if we calculate the synchrotron and inverse Compton cooling timescales and the flux suppression due to that, we will not be able to reproduce the SED evolution. So we interpret the radio evolution from WPP as a result of shock propagating through a dense shell of medium and coming out. Now here the flux suppression will be due to free optical depth effect, which will put a constraint on the density. So here we show the CSM density profile of WPP in red star symbols and all other LF bots in circles. Now, there are multiple striking features in this density profile. One is that all the LF bot density profiles align in very similar space in this plot in terms of normalization as well as in terms of the profile. And this very similar evolution, very similar density profiles up to 10 to the 17 centimeter or so should indicate that these are similar evolutionary phases setting up these environments. Now, there is also indication of relatively flat density profile at smaller radii. As you may note, there is only 2018 cow and WPP with such extensive observation. And you see complementary results from near IR derived densities, nicely complementing the radio inferred density estimates. Now, here we show our view of WPP and its various emission component. This is in a central engine driven progenitor scenario inspired by the models proposed by Metzger 2022 and Daiichi Tsuna's 2025. Now, both these models are different in terms of their astrophysical context, but invoke a super Eddington accretion disk onto a compact object. Now, the super Eddington disk would also drive disk wind outflows that can reach up to 0.4 C. Now, the X-ray emission is coming from the central source, and the varying Compton hump that we see in WPP goes quite well in this scenario, as we are seeing the X-ray emission through the expanding asymmetric ejecta. Now, the optical emission is reprocessed X-ray from a reprocessing layer. We stay agnostic about the nature of the reprocessing layer. And radio emission is coming from the fastest moving material from the disk wind outflow, which are much above the optical photosphere. Now, this is what we built from WPP. And as I mentioned, there is only a few number of events with detailed multi-wavelength observation, which limits our knowledge of understanding these transients as a class. So we certainly need more objects to be discovered in the coming era, plus multi-wavelength coordinated observation to understand their environments, energetics, and progenitor scenario. Thank you, and I'll take questions.
All right, thank you, Nayana, for the nice talk. Questions for Nayana? All right, I guess I have a question about how you measure the CSM properties with the near-infrared observations. Are you fitting something to the dust emission or?
Yes, so basically the near-infrared slope and the luminosity will translate to the density profile.
So you're fitting some kind of model to the slope of the near-infrared?
Yes.
Okay.
Yeah.
Okay, cool. All right, awesome.
Okay, thank you. So I thought it was a really interesting figure you put up of showing the mass loss rates for all the LF bots that they line up perfectly. I think you previously said that you were making kind of some assumptions about the conditions of LF bots, and have you looked at like maybe if they aren't all similar in some of that physics, could that shift things here, or is this a pretty secure model independent, assumption independent result?
So these densities are certainly have strong dependence on the assumptions. These are coming from synchrotron self-absorption models of radio SCDs, where the major dependence on this density come from the assumption on shock microphysical parameters. So what fraction of shock energy is going to the magnetic fields. So that is huge in terms of absolute values of these densities. But the overall trend and the universal behavior remains the same, because all the numbers are inferred by assuming the same epsilon value. So if we are off in terms of normalization, we are off by the same amount on all events.
Okay, final question. Oh, let's see. I don't know whose hand was up first.
I think I saw your hand.
Yeah, okay, all right. Sure, okay.
Very nice talk, Nayana. So a question about the late time values of the CSM. If I remember correctly, 18 cow, the SCD is very broad and the optically thick part is very shallow. So that suggests that we might not see directly the synchronal self-absorption peak. What do we know about the other events or your event And how does that influence what we see in this diagram?
That's a very good question. So all LF boards, all radio bright LF boards has this classic feature of their synchrotron self-absorption part is flatter than the due to the 5/2 power law that we would expect for pure synchrotron self-absorbed sources. So it is possible that there are inhomogeneities in the emitting medium that is leading to flatter than the classic 5/2 power law, but we use the standard synchrotron assumptions to get these numbers. So we are, there is that uncertainty between between that flat new optically thick slope.
All right, thank you for all the questions, and let's thank Nayana again.